in a way that you intend it to, and there are many ways where things can go wrong. So uh, in order to do so, we have built a simulation of sorry we've built a simulation of this world, and we've given control for this. So we have on the top right again Tom, and I'm controlling him. I'm choosing arrow keys to move him around, and I have Jerry, again another entity which you can move around, and the green around it is to depict the sound sensor's area of influence, where if if one enters the other's influence, then you can signal the end of you can terminate the game, thereby giving Tom, because Tom happened to catch Jerry, he gets his positive reward, and Jerry gets his negative reward associated to the states. And yeah, so the main idea is we have now successfully transferred at least most of what we've learned from the real world and taken them all into account in modeling this simulated world, and henceforth we will use this simulation as a way to study their behavior, which would otherwise take a really long time to witness as the robots. So now that we have been moving, so I've been controlling the robot, I've been instructing it earlier, we need a learning algorithm, and in this case we have two flavors that have been compared in this thesis, and one is a greedy approach where you have epsilon value, and this epsilon value is what determines, say epsilon tending to 1 is the agent acting very randomly, and the closer it is to 0 is it's exploiting. So a greedy means you purely exploit, and you spend very little for exploring, and so you follow a policy which is optimal. So you only follow a policy which is optimal until now that you found. And the idea of policy is essentially, it's the golden rule that has been learned up until this point. So at every point the agent clarifies and makes sure it follows the policy that it has learned, and that is the behavior of the agent in some sense. And the other approach is called Thompson sampling or posterior sampling, and here the objective is you randomly select an action according to the probability it is an optimal action. So it's one of the oldest heuristics for balancing. So there is this need to balance explore, how much do you explore, how much do you exploit, and in the greedy approach we had this epsilon value, and there are also ways by which you can dither this value, and so it's somewhat like simulated annealing, where you heat up, make it move randomly, and then you start settling and cooling down the epsilon value. I mean, I haven't done that, but that's possible ways to work with the epsilon value. And in the case of Thompson sampling, we instead sample from the MDP. So this essentially means you choose state, you have a probability distribution, and in this case we consider what is called a tabula rasa learner, which is a blank slate learner. So you have no idea about anything, and you need to start associating by sampling from what you know in order to update the posterior of the distribution, and it goes on in a loop. So you keep updating your prior, and you start understanding your what you're learning in this. So we'll see some analysis of these two, which will give us a better idea of how they are in action. So the next is okay. So here we have the greedy Tom and a greedy Jerry. So here we also, okay, so in order to analyze how these games, so now that we know, we've constructed the MDP and we start these games that run for a particular amount of episodes, I think it's better we look at it closer. Okay, so what we see here is this is what I would like to call an evolving heat map, and this keeps, so now we have moved on to a 10 cross 10 grid. So these are the grid columns, these are the grid rows, and like we saw earlier, and so this is the state where, sorry, not this is the state where, because there's a buffer wall around, this is the state where Jerry starts, and this is the state where Tom starts. But this is Jerry's perspective of what he has learned, and what do these values signify. So all this takes into account is the final position that Jerry secures a victory in Jerry's case. But here it's in Tom's case where he caught Jerry. So when you look at the evolution of such a heat map, it has a small story to tell, but you can also not only look at the visualization of the end game points, but also the strategies that are happening. So here we notice around 100 games Jerry has secured a win in this particular position, which Tom in this case has started to discover, because they cannot collide into each other, it's always next to each other, these positions. And as we see through more learning episodes, it shifts its new hiding spot, so to speak, to this part of the grid, and Tom picks up on that. And so the epsilon greedy, this shows how Jerry is bent on just exploiting that one particular hiding position and keeps going to it, and Tom slowly starts to figure it out. So the main idea is to get an understanding of this kind of an evolving heat map, and what we can see when we look at a policy. So here we again have the same simulated world. So this is episode 2000. As we saw on the left, we saw the plot which kept evolving Tom and Jerry across 2000, 4000 till 10,000. So this is just a small, so you open the hood and you just have a peek at what kind of a game is happening. And this is like, you get to view the policy. And what we can see is Jerry has come up with this strategy of circling along the corners of the wall, and through, so I mean, did you guys catch that? Or I don't know, sometimes it's too fast and I've got so used to it, so I'm not sure if everyone can follow. And around 3000 episodes, Tom is able to now work out to cut that strategy, so to speak. And we also have, yeah, so I think the main thing is this particular, when we put now these two algorithms against each other, that is the PSRL Jerry, which is trying to balance exploring and exploiting better, and we have a greedy Tom. Here we can see immediately there is something more interesting than what we saw earlier, which was in the earlier case we saw them evolving, Jerry finding a spot, Tom uncovering it, Jerry finding another spot, Tom uncovering it. But in this case we see yeah, so we see, sorry, I didn't, yeah, so what we see is, okay, I'm sorry I didn't, so what we see is there is this very evident track that Tom is doing something interesting, and in order to open up and see what it is doing, we kind of can notice this kind of a patrolling strategy that Tom has started to, the greedy Tom has started to make a lot. He starts to use the strategy a lot, and it's very evident that he has found some kind of a strategy to always catch Jerry, and we can notice this on the value plot where he has caught Jerry multiple times on this patrolling path, and at the same time Jerry is, as we can see, spreading his options across the region where Tom is not hunting. So very clearly knowing that there is something in this region that it should avoid. And yeah, and here one of the very interesting strategies that Jerry unveils is hiding at the spot where Tom starts, and Tom continues to keep prowling. This is around 6,000 episodes when you look under the hood, and we can see how Jerry finds a perfect hiding spot in the corner where Tom starts, and Tom just goes about searching. And this also is very reminiscent of what is called reward hacking in RL literature, where you're able to see that Jerry looks to want to stay in a particular point, because up until this point we have only given 4 actions, that is north, south, east, west, and so another action that is to stay in the same place, it can also be included, and some tests have been run to accommodate an extra action apart from the moving actions. So this is again just to show how Tom and they sample from the MDP and they move, and in this case we can notice how if we compare a PSRL Jerry to an epsilon greedy Tom, we can immediately see the lack of exploration that the greedy algorithm, yeah, it doesn't explore as much. So yeah, so when we run like a lot of these agents against each other, and in this case we keep track of who's winning, like that's important to know. One of the important things, apart from knowing where these hiding spots or these patrolling strategies are, who is winning. And it seems that Tom, in this particular setup, it's heavily Tom favored, and the ratio, so this is running these agents against each other for like 10,000 episodes and keeping track of how many episodes did Tom win, how many episodes did Jerry win. And yeah, I mean, I think you get the idea. The main thing is to keep to understand the value plot and the policy plot. Okay, and now so what are some of the questions that I couldn't accommodate during the time of this thesis? So will it be possible for these agents to learn like any sort of map? Like in this case we restricted it to only an obstacle-free case, whereas you want to now add static objects in this mix and see if it's able to design the floor of a map and adapt to it, and also the possibility of moving from such a deterministic and strict kind of a system to a continuous one.